Boom! Yes, folks, Hume again. How are you going? So welcome to this our first in a series of videos where we will deal with the topic of differentiation. All right. Now, differentiation is a very involved topic where this maths is concerned, where the calculus is concerned, and there are so many different angles we could approach it from. Differentiation means different things in different contexts, and the applications of differentiation are very, very numerous and varied. All right? What we will try to do here is to give a few basic ideas and concepts. So we're not going to take the approach which is taken very often, which is to just slap you with some formula until you learn that. No. We want to understand certain basic concepts where differentiation is concerned. And after we do that, then we will get into some of the formulae and the memorization and the application and the questions and the problems and whatever. All right? So, on the board here, you have two graphs. You have on this side a graph of the line y is equal to 2x. And on this side, you have a graph of the line, of the curve, y is equal to x squared. Before I continue, this is a trivia question. Did you know that a straight line is also a curve? Haha, I bet you didn't know that, right? In the precise mathematical language, the precise language of mathematics, a straight line is a curve. A straight line is a type of curve. In other words, the set of straight lines is a subset of the universal set of curves. If we want to use some language from sets, right? Going back to mathematics now. All right? But of course, in practical terms, a straight line is not a curve, and it could distinguish between the both of them. So in other words, we could say, mathematically speaking, that a straight line is a curve of degree 1. We could say that, in other words, a straight line is a linear curve then, right? A straight line is a curve of degree 1. We could say that a straight line is a curve without any curvature, right? That's just beating the thing to death, literally. Beating it. In other words, beyond a certain point, you start to lose the practicality for regular day-to-day purposes. Right? Of course, beyond that, people who deeper into it will understand when we say that a straight line is a curve, but for practical purposes, we know that a straight line is a straight line and a curve is a curve. Right? Just a little brain teaser to start, right? Just to fire some neurons in the brain, so to speak. Right? Just to give you a little touch of a much bigger picture that we're going into. All right. So, where the straight line is concerned, we know that there's this thing that we refer to as the gradient of a straight line. All right, we refer to as the gradient of a straight line. We know that the gradient is defined as the change in y divided by the change in x. We could, listen, man, there are so many ways in which we could say this. I had us to write them down, right? Excuse. We talk about the change in y over the change in x. We talk about the change in y per unit change in x. In other words, every time x changes by 1 unit, y changes by a certain amount, either positive or negative. That essentially is what we refer to as the gradient. In other words, the gradient is the ratio of the change in y to the change in x. All right? And when we make the change in x equal to a unit, 1 unit of x, then we refer to it as a unit change in x, and that is what we get as the precise definition of the gradient. We could also refer to the gradient as the, the average ratio of the change in y over the change in x. We could talk about that too. All right? So let me run through these things again. We have the rate of change. No, sorry, not the rate of change. Let me leave that out for now. The ratio of the change in y over the change in x. That is what the gradient is. Right? But we could use different language to describe that. Right? We could talk about the gradient of a line segment. Right? And of course, we could talk about the gradient at a point on a straight line. All right? The thing about the straight line though, in fact, before I say that, I'm going to do a quick demonstration, right? The idea is that the relative change in y over the relative change in x is what we refer to as the gradient. So, whether we're talking about the change from here to here, so this change over this change is the gradient, or we could talk about the change from here to here, right? This change over this change is the gradient. Or we could talk about the change from here to the change in here. We could talk about this change here over this change here. That's the gradient too, right? So in other words, the relative change between y and x, between any 2 points on this line, is what we refer to as the gradient. So the gradient is, we refer to as the gradient as, gradient is change in y over change in x. That is basically what it is. Right? We know that the regular formula that everybody is accustomed to by now is y2 minus y1 over x2 minus x1. That's the change there. Change in y over a change in x. The difference between the two y coordinates, in other words, the vertical difference divided by the horizontal difference, the difference between the two x coordinates. Right? You ratio one thing divided by the other. The ratio of the change in y over the change in x. Now, we're going to introduce some notation that will carry forward in the discussion when we start to talk about curves, when we start to talk about differentiation. We could write this gradient as, let's see, blue, right? We can write the gradient, let me use the letter m, which we're familiar with from our work on straight lines up to this point. Your gradient m is equal to your change in y over your change in x. Right? This triangle is referred to as delta, that's capital delta, right? Delta y over delta x, or if we want to use the common letter, right? Delta y over delta x, right? You know the curvy thing we're talking about. So this is the common, this is the capital. Delta is what we use to refer to as the change in y divided by the change in x. That is essentially what we refer to as the gradient of a straight line. The thing about the straight line though is that because of the, let us say, the relative simplicity of the straight line, all of these things are one and the same. So when we talk about the gradient of a line segment, right? The gradient of any line segment on this line, we could talk about the gradient of the line itself, the whole line, right? We could talk about the average gradient between any 2 points. We could talk about the gradient at a single point. I'll leave out anything? No. Right. So in the case of the straight line, at any point and at all points on the line, all of these different ways of describing the gradient have exactly the same meaning, have exactly the same connotation. All right? That, however, is not the case for the curve. So we're going to talk about the curve in a little bit, just to demonstrate the whole idea of the difference between the straight line and a curve. Because with the straight line, the gradient never changes. That much we know. All right? We also know that we have the concept of a straight line. We don't have we have the concept of the gradient of a straight line. There is no such thing as the gradient of a curve. You can't have a gradient of a curve. A curve, by definition, does not have a gradient. you could define the gradient between, you could define the gradient of the line segment between 2 points on a curve. You could do that. You could define the average gradient or the average ratio of x and y. The average change in y over the change in x between 2 points on a curve. You could define that too. And you could also define the gradient at a single point on the curve. That is where you start to move in the direction of what we refer to as differential calculus. We'll come to that soon. So we start off from a point of familiarity. We start off with something you know already, right? If you're doing art maths, by the time you get to starting to consider differentiation, there's no way straight line should be a problem. All right? So there are certain things that I discuss here and are taken for granted as an art math student, that you know what the gradient of a straight line is, that you know what the equation of a straight line is, that you know how to find the gradient of a straight line, that you understand that in the case of a straight line, the gradient between any 2 points on this line will always be the same, regardless of where you choose those points. All right? And to that general knowledge, we add one single concept, which is, following from all of that, we can define the gradient at a single point anywhere on this line. The gradient at one instantaneous point. Vocabulary again. Instantaneous gradient. Right? So, as opposed to describing the gradient over a range, let me say a range of points. Right? Between the gradient between 2 points on our line segment. All right? So again, this is where we move from straight line into something else. Up to this point, we have traditionally defined the gradient as the gradient of a line segment. And that is what it is really. But think about this carefully now. If the line segments get progressively smaller, what happens to the gradient? We'll deal with that across here, but let me deal with it here first. Line segment. Right? From between the point 1, 2 and the point 5, 10. Let me move the points closer. 2, 4 and 4, 8. And let us make the line segment progressively smaller until we bounce up at a singular point here. The gradient at that point is also a concept, is also an idea. So you have the gradient of a line segment, right, in general. And as you make the line segment progressively smaller, you get to what we refer to as the limiting case. Know the vocabulary. That is also important. We will deal with that a little later. You get to the limiting case where the line segment actually becomes a point, where the length of the line segment is effectively 0. That is what we refer to as a point. All right? So we could describe a point as a line with 0 length. Right? You know, in maths, these things are hard to define. Ask somebody to define a curve. You might get something on Google, you might get something on Wikipedia, you might get some precise mathematical definition that means nothing to anybody who not studying maths above a certain level. Right? Ask somebody to define what a line is. Ask somebody to define what a point is. It's hard to really say, but you know a line when you see one. You know a curve when you see one. You know a point when you see one. All right? These are the things that we had to deal with in maths. These are the things that make maths interesting. These are the things that make maths nice. Right? So we have discussed a few general concepts with respect to the straight line, things that we're already familiar with. We twist it and we turn it a little bit. We add some new vocabulary. And now we're going to apply the same ideas to the curve. And as you would suspect, just by looking at the difference between the two graphs, that things that obtain over here, in the case of the straight line, may not necessarily apply over here in the case of the curve. And we use a simple curve, y is equal to x squared. So what I'm going to do here is demonstrate the difference between the straight line and the curve with respect to certain basic concepts. The first concept is the concept of the gradient of the entire line. We could have the gradient of the entire straight line. And because the equation of this line is y equal to 2x, we know instinctively by simply looking at the equation that the gradient of this line is 2, which is to say that the ratio of the change in y to the change in x is equal to 2. What that means, and I'm going to rub off these guys here now. What that means is that, let me say m, right? We start from a point of familiarity, is equal to the change in y over the change in x, which is equal to 2. And we could say 2 is the same thing as 2 over 1. So anytime your x change by 1, there's a corresponding change of 2 in y. Of course, if we had a negative sign in front, it would mean that the y would change in a downward direction as opposed to changing in an upward direction. All right? The gradient of 2 means that the line goes like this. A gradient of minus 2 means that the line goes like that. Excuse. All of these things I would have covered in a whole lot of detail in my maths videos in the mathematics website. All right? Hint, hint. All right? So, the gradient of the entire line segment, no matter which 2 points you choose. So in other words, the gradient of the entire line segment or the gradient of any line segment on this point, on this line, sorry. Even in the case where the length of the line segment is 0, which constitutes a point, the gradient is equal to 2. Every time your x change by 1, your y change by 2. There is no such concept in the case of the curve. There is no concept of the gradient of a whole curve. You can't find the gradient of a whole curve. You can find the gradient between 2 points on a curve. And just as in the case of the straight line, when the distance between those 2 points ends up being equal to 0, then you have the gradient at a point, which is the instantaneous gradient. Now, of course, the expression of those concepts will be different across here to what they will be across here, and we're going to demonstrate that now. So we know there is no concept of the gradient of a curve. So let me demonstrate the gradient between 2 points on a curve. We could have the gradient, let us say, we could define the gradient of this line segment here. Right? Line segment between 2 points. Line segment between the point 1, 1 and the point 3, 9. We could define that gradient. So we could define the gradient of this line segment, which would also be the same thing as the average change. In other words, the average change in y over x between these 2 points on the curve would be the overall change in y divided by the overall change in x. All right? So the average change, or the average ratio, very important, all right, of change in y over change in x will be equal to the total change in y, total change in y over the total change in x. right? Pardon the little total change in x. This is the 0.416. Now, here's where things start to get nice. 4, 16. All right? Here's where things start to get nice. Whereas on the straight line, the gradient between any two line segments, any 2 points, will be the same as the gradient between any other pair of points. We look at the curve and we immediately get a sense that that is not the case. Because if we do this, if we take, starting from the same point 1, 1 here, and we come and we do this, right? So we have a new line segment in blue now. Excuse the relative lack of straightness of the line. The lack of straightitude. Yeah, that is my new word here now. Right? Oh, not straightitude. The lack of rectitude. Rectitude is a nice word that means straight. You get some vocabulary in your session too. Right? Nice. So forgive the paucity of rectitude in my blue line, but I just want to demonstrate something here. All right? So now we have a new change in y over a new change in x. So in other words, the gradient of the line segment between the 0.11 and the 0.416 is a different gradient. You could see that. This gradient in red is not the same as the gradient in blue. And if we do the same thing between the 0.11 and the 0.525, we get yet a different gradient. Let me do it just for the sake of argument. Sorry, I don't have the orange marker, but that coming just now. All right? Watch it. You do this. All right? Again, forgive me if the line not as straight as I want it to be, but all you know what I'm trying to do here. Hey, we ain't do so bad. All right? And then we come across like this. And we do this. All right? So this gradient, this change in y over, let me say, this change in x is a different ratio. So with the curve, you get a very clear sense that unlike the straight line, where the gradient between any 2 points will be the same, any 2 points you choose on this line will give you a gradient of 2. That is not the case over here. You get a different gradient depending on what points you choose. So here we're going to do. We're going to clear this side of the board because we will need some space to do the calculations associated with this curve here. Yes, I know the board is a little messy, but I want you to pay attention and you will see exactly what I'm doing. All right. So I think we finished with the straight line for all intents and purposes, but I will leave it there in the corner just in case we need it again. So we'll try to use this space here to do the calculations. All right. So the gradient in green. The gradient in green is the change in y over the change in x. All right. The m in green is the change in y over the change in x. Triangular, looking so triangular, but we could fix that. Y2 minus y1. All right? 25 minus 1 over 5 minus 1 equal 24 over 4, which is equal to 6. That's the gradient in green. The gradient in blue, that's the gradient between the 0.11 and 416. All right? The m in blue is equal to change in y over change in x, which is equal to 16 minus 1 over 4 minus 1, which is equal to 15 over 1 over 3, which is equal to 5. Different gradient. And then we come down out to our good friend in red now. Gradient between 1, 1 and 3, 9. So m is equal to the change in y over the change in x, which is equal to 9 minus 1 over 3 minus 1, which is equal to 8 over 2, which is equal to 4. And if we take the gradient between these 2 points, between the point 1, 1 and the 2, 4, you'll get that that gradient is equal to, where we can squeeze that, man? Let me try and squeeze it in the corner here. That gradient is equal to change in y over change in x, as equal to what? Excuse, 4 minus 1 over 2 minus 1. 4 minus 1 over 2 minus 1, which is equal to 3. So, you see a progressive decline in the gradient with the line segment from here to here, the line segment from here to here, the line segment from here to here, and the line segment from here to here. Alright? So, we have demonstrated, now again, this is not what the actual graph of y equal x squared looks like. The actual graph is actually a much steeper curve if you have the same scale on the 2 axes. Alright? But I'll use a different scale on the x-axis to the scale on the y-axis to kind of spread the graph out a little bit. Right? All doing add maths. So all them concepts I just running through, I'm not even explaining that here. Alright, we will deal with that in maths. Alright? So, and as the same thing applies with the graph of the line of y is equal to 2x. Y is equal to 2x is actually a very steep line, something like that. Alright, again, I just mentioning that, so when you go on wherever you just go on the internet to get your graphs and things, don't expect a graph of y equal to 2x to look like this. If you're using the same scale on the 2 axes, don't expect the curve of y equal x squared to be coming all out here if you're using the same scale on the 2 axes. The scale is important, but this video is not the place for that. So, we continue. So, using regular integer points, points that we could actually do the calculations for very simply, we don't need any calculator for that. We could see that the gradient is different. And if we do the same thing on the straight line, just for the sake of demonstration, the gradient between these 2 points, 4 minus 2 over 2 minus 1, 2 over 1 is 2. The gradient between this point and this point, 6 minus 2 is 4, 3 minus 1 is 2. 4 over 2 is 2. The gradient between the point 1, 2, and 4, 8. 8 minus 2 is 6, 4 minus 1 is 3. 8 minus 2 over 4 minus 1, 6 over 3 is 2. And if we do the same thing between 1, 2, and 5, 10. 10 minus 2 is 8, 5 minus 1 is 4. 10 minus 2 over 5 minus 1, 8 over 4 is the same 2. So I'm saying the thing, and I'm repeating the thing, and I'm showing you the thing, and then I go say it again. So in other words, you wouldn't really have my excuse to say that you didn't understand what I say if you was paying attention. That is a variable. Right? And we know that is a whole conversation by itself. But once I make this video and put it out, the ball is totally in your court. I'm not stressing out myself to beg people to pay attention. What I can promise you is that if you pay attention, there is a whole lot of stuff you'll pick up here. And a lot of the stuff you'll pick up here, you wouldn't pick up elsewhere. But that is a separate conversation too. Alright? Nice. So, we are sure now, if we were not sure before, using the same x coordinates on both axes, naturally you'll get different y coordinates because it's a different graph on this side to the one on this side. And because this is a different type of graph, a different type of curve, if you will, you can see with your eyes and you can work out with the calculation that it is not true across here that the gradient between any 2 line segments will always be the same. In fact, as you go as the x increases, the gradient actually increases, right? And on the flip side, as the x decreases, the gradient decreases. So, in the same way that we could define the gradient between here and here, and then define the gradient between here and here, and then define the gradient between here and here, and then we define the gradient between here and here, and we could move the other end of the line segment closer and closer to this point, and the gradient will still be 2. So you start here, and then you come 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 anywhere until you actually get to the same point. Even at the one singular point, 1, 2, the gradient is still equal to 2. On the flip side, the gradient between here and here of this line segment, the gradient between these 2 points is 6. And then you take this point and you move along the curve and you come here. The gradient between this point and this point is 5. And then you take the same point and you move along the curve and you reach here. The gradient between this point and this point is 4. Right? And then you take the same point and you bring it here. You will get that the gradient between here and here is 3. So what will happen as we move this point between here and here until it actually gets to this actual point here? Well, let me do it and see. So to do that, now we are at the point where we have to clear the board. There is no option, because I want to come on this side and actually take this region of the curve and make it a little bigger here, and we could do some calculations and we could demonstrate some things. Right? So we could close off this particular video here, because we have discussed some basic ideas with respect to the gradient of a straight line, things that we are already familiar with. We have added to the discussion because we're starting to move in a particular direction, where we're talking about the same concept of gradient, but we're applying it to a curve. All right? We agreed that the concept of the gradient of an entire curve just simply does not exist. However, we could find the gradient between 2 points in a curve, the average gradient, so to speak, right? The average change in y over change in x, the average ratio of the change in y over the change in x. And we show the difference between what happens in the case of the straight line and what happens in the case of the curve where that is concerned. So we establish that in the case of the straight line, it doesn't matter how long the line segment is. It doesn't matter the distance between the 2 ends of the line segment, between the 2 points. The gradient will always be the same. We know that instinctively by now. We know it so instinctively that even to hear me discuss it like this, it still requires some thought. On the other hand, where the curve is concerned, the curve of y is equal to x squared, we have seen by observation and by calculation that the gradient or the average ratio of the change in y over the change in x between any 2 points on the curve depends on the location of those 2 points. Alright? So the gradient between here and here is different to the gradient between here and here, is different to the gradient between here and here, is different to the gradient between here and here. And yes, the gradient between here and here will also be different. And the gradient between here and here will also be different. So in other words, any 2 points on this curve will have its own unique average gradient between those 2 points. And of course, what that suggests is that Unlike the case of the straight line, where the gradient at any singular point is the same regardless of where the point may be on the straight line. What it suggests is that the gradient at any singular point on this curve will be different. So in other words, just as the gradient between any 2 points, the average, just I have to be very careful with my language here now. Just as the gradient of the line segment between any 2 points on this curve will be unique, every pair of points will have a unique gradient between them on the curve. The same idea applies for the point. Every single unique point on this curve will have a unique gradient attached to it. Will have a unique gradient. We will discuss in a little more detail subsequently to this the concept of the gradient at a point. By now we should have an idea of it. It just simply shorten the line segment, that is all. As you shorten the line segment, you approach what we refer to as the limiting condition. The limit is actually the point. Alright? But we will deal with all of that subsequent to this video. So stay tuned, look out. We have more coming up.